three-phase system, we have the phases twisting around each other, and the middle phase has a wiring reversal of polarity to create a 1/6 cycle difference between the inner layer and the outer layer. This raises the impedance of each phase by mutual induction with the neighboring phases, and we call this a 666. On this 666 machine, we have 3 gate secondaries, mega cable spiral wire. There's one, and there's one. And we're receiving a volt from each one, adding 3.1 volts in series. Now, because the coils are in series, the same amperage and the same phase angle are all uniformly collectivized in this circuit. We call it a communist electrical circuit. For the analogies that everything is collectivized and everybody marches to the same orders derived. Those orders are derived from a combination of all 3 of these sources, and the phase angles between them sources are shown by the voltage meter. At any point in time, then, we can route this back into the field we have an alternator, motor running an alternator. And we have that voltage that we obtained from the communist system, collectivized 3 volts going into that diode system, producing a DC pulse into the alternator itself. And we have an amperage meter there for that branch of self-excited current. Okay, we're going to do one more thing here. Now, we're going to show how the placement of high induction coil secondaries will ballast that voltage. It's at 3.1 volts. Phase number 2's coil, and phase number 1's coil. Now we see that that's gone down to 2.2 volts. Now we're going to self-engage the field. And once again, it's not working. We went through this on the last video. Well, it appears to have worked. The voltage dropped from 3.1 volts to 2.4 volts. But over here, it's only showing 0.4 of an amp. This is what I refer to as the non-linearity of the field resistance at the low end. If we took that 0.05 amps and divided it by the voltage that we've got across it, we'd find that the field resistance is phenomenally higher than it is in actual operation. So now we're going to get the field into the mode of actual normal operation. And what we're going to do over here is show where we're at in our operation. We've got 1.3 volts across the board. We'll turn those amperage meters back on. an amp, 0.3 of an amp, being consumed at 1.3 volts. We'll disconnect the feedback loop. We now find that it went down to 1 volt at 0.24, 25 amps. Reconnect the feedback loop. And we're back to where we were. Now what we're going to do, we're at 1.5 volts. At any time it may take off, but what we're going to do is we're going to help it along. We're going to help it along by raising them coils there. Now we have the process. We have the process lighting a 12-inch xenon bulb. We're about 6.6 to 7 volts on our stator lines. 1.1 to 1.5 on our amperages, and we got half of amp now into the field. Now look over here. We've got 5.8 in the vicinity of 5.8 volts, enabling that half of an amp into the field. Well, that's not the same resistance reading we started out with at the very low end. And so then we'll close out here to show that we've got a 6 to 7 volt self-engaged field lighting a xenon bulb. If this can be done, we can surely run a Tesla coil with the same process. We'll try running a bipolar Tesla coil perhaps. Catch-22 about the matter is in order to gain the voltage, you have to back away from the magnetic flux that causes the voltage.